Stanford University.
Are there any other questions that I can answer in 5 minutes?
You mentioned last week that a person traveling near the speed of light would measure at longer wavelengths.
Well, depends on which way it's going. If the light wave is going that way and you're moving with it, then the wavelength looks longer than if you were standing still. If you're moving the other way, it looks shorter. That's the Doppler shift. That's the Doppler shift. And all right, let me tell you how you can work it out. You can work it out just from geometry, from the geometry of the Lorentz transformations. Here's what you do. Say, all right, first of all, let's do the usual drawing of two coordinate frames. One of them is at rest, that's your frame, and my frame is moving to the right. And so my frame looks like this. Let's draw on one more thing. Let's draw on the speed of light. Just like that. All right, now imagine that there was a wave. And think about, here's the wave. And the wave is moving to the right. As it moves to the right, we can follow the peaks of the wave, the high points of the wave. And I'm going to draw them in red. They're also going to move with the speed of light. So they're going to look like this. Notice that as you move up, meaning as time goes forward, the wave moves to the right. So that's a right-moving wave. And what's the wavelength? The wavelength in your frame of reference is this distance over here. The distance between successive maxima. What's the wavelength in my frame? The wavelength in my frame is this distance, but this distance as measured using relativity and using the Lorentz transformations. In other words, this distance here is the distance between the two maxima at what you call an instant of time, and the wavelength to me is the distance between the two maxima at what I call an instant of time. So if you work out the Lorentz transformations and you look along here and ask what's the distance between these 2 points in your or my reference frame, and compare it with the distance along here, you'll find it different. And that would give you the Doppler shift. You have the tools to do that. You can do that. You know the Lorentz transformations. You can figure out what let's say the wave, well, here's some wavelength, some particular wavelength. You can figure out what this point is. You can figure out what this point is. And you can ask what's the x prime distance between them. X prime is my coordinate. X is your coordinate. The x distance between these is lambda. And you can figure out what the x prime distance is, and that's the way to calculate the Doppler shift. So I recommend it as an exercise in working with Lorentz transformations. Yeah.
Is the next course in a sequence going to be next fall?
Yeah.
There's nothing this summer?
No.
And what will the topic be? Do you know yet?
We'll take a vote. I'm not sure. I think there's Possibly general relativity. Possibly more quantum mechanics. Our coverage of quantum mechanics was reasonably deep, but not very broad. Having not gotten to the harmonic oscillator, that's a bad thing. So I think before we study quantum field theory, we do have to study more quantum mechanics. But I'm not sure which way to go next quarter, and I haven't decided yet.
Can I make a small request?
Yeah.
Whatever it is that you have, could you cover infrared and ultraviolet connection?
Yeah. But not yet. We have to do general relativity first. That's a gravitational issue. We haven't studied gravity. That's an issue of a combination of quantum mechanics and gravity. We may know enough about quantum mechanics at this point, but not enough about gravity.
The scales are not the same on x and x prime, is that correct?
What do you mean the scales are not the same?
We can't just look at the black.
No. You can't just look at the blackboard. You have to do the Lorentz transformations. Right. Right. Okay, how do you do it? Let's make this wavelength 1 just to simplify. So this is 0, this is 1, this is 2, and so forth. All right, now I would like to locate what this point is. It's clearly important for me to locate where that point is. This point is x prime equals 0. That's the same as, which is it? T equals Vx. Do you remember that? That the surface T prime equals 0 is the same as T equals Vx. Let me remind you why. The Lorentz transformation involves T prime is equal to T minus Vx over square root of 1 minus V squared, right? All right, now supposing I want to know where T prime equals 0 is. T prime equals 0, that's what I call an instant. Happens to be the instant T prime equals 0, but that's okay. And that's clearly T equals Vx. So this is T equals Vx. And what is this line over here? Well, first of all, what is this line? X equals t, moving with the speed of light. C equals 1. That's x equals t. What is this one? Oh, come on. It's easy. All right. X equals t plus 1, right? Okay, so we're at the intersection of x equals t plus 1 and t equals Vx. Let's work it out. Let's see what that point is. X equals t, which is Vx, plus 1. Or x times 1 minus v equals 1, or x is equal to 1 over 1 minus v. That's the x of this point. And what about the t of this point? Well, if we know the x of this point, let's see, if we know the x of this point, we can read off the t. T is equal to v over 1 minus v. All right, now we would like to find out what, the simplest thing to do now is to figure out, we know t and we know x. What I'd really like to know, what would I really like to know about this point over here? I'd like to know x prime. I would like to know the distance between successive minima in my frame, the primed frame. So we go to the primed frame. X prime is equal to x minus vt over square root of 1 minus v squared. And now I just plug in for x and t what I have here. Do I really want to do this? Yes, I do. X prime equals x 1 over 1 minus v minus v times t. So that's v times t minus v squared over 1 minus v, all divided by by square root of 1 minus v squared, right? Did I do that right? I think so. Okay, so let's see if we can simplify it now. We have 1 minus v squared, 1 minus v squared, divided by 1 minus v, and also in the denominator, I also have square root of 1 minus v squared. Okay. 1 minus v squared is the same as 1 minus v times 1 plus v, right? That's 1 minus v squared is 1 minus v times 1 plus v. And so these cancel out. What else can I do with it? Well, I can put this in the square root, just by squaring it and then putting it in the square root. And the whole thing becomes square root of 1 plus v times 1 plus v, that's 1 plus v squared, divided by 1 minus v squared, which is 1 plus v times 1 minus v. So the answer is square root of 1 plus v over 1 minus v. That's what x prime is over here. Is it bigger than 1 or smaller than 1? It's bigger than 1. It's bigger than 1. So my reckoning of this distance gives me something bigger than 1. You said the wavelength was 1. I say the wavelength is square root of 1 plus v over 1 minus v. Okay, so that's the calculation. Whew, wow, okay. Does that answer your question, Warren? Good. Okay. So it's all there in these pictures. Just draw the picture of the thing you're trying to figure out and then convert it into some simple equations. Good. Now, let's put this up. This, of course, is the relativistic Doppler shift formula, square root of 1 plus v over 1 minus v. And to really be correct about it, this is v over c, and this is v, not correct, it was correct, but to put units in, which is the same as square root of c plus v over c minus v. What do you think happens if you're going in the other direction? If I was going in the other direction? You would just change the sign of the velocity from plus v to minus v. That's just going in the other direction, minus v. And you would get square root of c minus v over c plus v. And now this is less than 1. So if you're shooting against the direction of the light ray, you see a shorter wavelength. If you're moving along the light ray, you see a longer wavelength. And what happens if your velocity gets up near the speed of light? Let's say this one over here. If your velocity gets up near the speed of light, then the wavelength gets bigger and bigger and bigger. And eventually, if you're moving with a light ray, if you could, the wavelength would look infinite. Okay. There's another way to, yeah, no, that's fine. Let's leave it that way. Okay. Good. All right, if there are no further questions, we will start tonight's lecture 10 minutes late. Fields and particles. Now, in quantum mechanics, fields and particles are the same thing, but we're not doing quantum mechanics. For us here, fields are fields and particles are particles. I won't say never the twain will meet, because they will meet. They will meet tonight. But they are not the same thing. In particular, we want to ask the question, if a field affects a particle in a certain way, for example, by creating forces on it that accelerate it or whatever they do, must it not also be the case that the particle affects the field? Well, why do I say that? Why does it have to be the case? Why, if A affects B, does B necessarily have to affect A? And that's built into the idea of action. That's built into the action principle, or into the Lagrangian principle. We can see it in a simple context. It's also called action and reaction. It's a basic idea. If A affects B, then B will affect A. So a simple example of it is to suppose that you had two coordinates. Now, you could have any number of coordinates, but let's just suppose for the moment two coordinates and an action principle. So let's call the coordinates x and y. And the Lagrangian is going to depend on x and y and x dot and y dot. X and y do not have to stand for the orthogonal coordinates, Cartesian coordinates of anything. They're just two coordinates. Now, and the Lagrangian depends on all of these. Now, one possibility is that the Lagrangian is simply a sum of two terms. The Lagrangian for x and x dot plus a Lagrangian for y and y dot. A different Lagrangian. I'll just continue to call it L. Might be the same, might be different. If this is the case, and you look at the equation of motion for x, let's write it down, then that equation of motion will involve d by dt of partial of L with respect to x dot is equal to partial of L with respect to x, and y won't get into it altogether. Likewise, if you write the equation of motion for y, x doesn't get into it. And so in this case, x doesn't affect y doesn't affect x. What can you say if you know that y does affect x? That tells you that the Lagrangian must be more complicated, and there must be things in it which somehow affect both x and y. For example, here's a Lagrangian. X dot squared over 2 plus y dot squared over 2. So far, they're completely independent. You could have a potential energy for x, no, minus, and maybe another potential energy, v prime, for y. So far, it's just a sum of two terms, an x term and a y term. X and y are not going to affect each other. What do you need to do if you want to see them affect each other? Put something additional into the Lagrangian which involves both x and y in a way that you can't unravel it. For example, just x times y. If you have x times y, then the equation of motion for x will involve y, and the equation of motion for y will involve x. If you have them both in the Lagrangian in a way which is coupled together in this way, there's no way that it's possible that one can affect the other without the other affecting the one. Right? So that's as simple as that. That is why if A affects B, B affects A. Okay, now let's come to the issue. Let's talk about particles and fields. We talked a little bit last time about how a field might affect the motion of a particle. That was just a simple model, but we'll go back to it. Let's go back to it. Talk about how the field affects the particle motion, and then come back and ask how the particle, the presence of the particle, affects the field. This is very much the analog of electric and magnetic fields affecting the motion of charged particles, and charged particles creating and modifying the electromagnetic field. For example, just by having a charged particle creates a Coulomb field and so forth. And those are not two independent things. They come from the same Lagrangian. So let's work out this example. All right, so let's begin with, let's suppose, first of all, that there is some field phi. Phi depends on x and t. For the moment, we forget about how it got to have the value that it has. Somebody solved some equations for phi and found out that phi of x and t has a, or measured phi of x and t, and it had some specific form. Phi of x, it might be a wave or it might not be a wave. How does that affect the motion of a particle? And for that, we're not going to ask about the dynamics of phi now. We're going to ask for the Lagrangian for the particle. This is the particle Lagrangian. So let's remember what it is to begin with. To begin with, it contains minus m times the square root of 1 minus x dot squared. What was this? This was the term in the Lagrangian that corresponded to an action which just added up all the proper times along the little segments of a path, multiplied by minus m. The integral of this Lagrangian, let's write it out. Let's write the integral dt, that's the action, that's the integral dt of this. And this is the same as minus m times the integral of the proper times from one end of the trajectory to another. All right, so that's the ordinary Lagrangian for a particle, but that doesn't have anything in it in which the field affects the particle. So let's put in something for the field, a simple thing, the simplest thing we can think of, simplest thing I can think of. Let me move this a little bit. And let me put minus m plus phi. Now, phi is a function of position and time in general. So it's a function of x and t. But we're imagining for the moment that it's a known function of the coordinates of the particle times the same thing again, 1 minus x dot squared. That's the Lagrangian for a particle. I could work out the Euler-Lagrange equations and find out how phi affects the motion of the particle. I'm going to do it, but I'm going to do it in the simplified approximation where the particle moves very slowly. Just as an illustration. I don't want to futz around with all the relativistic square roots of 1 minus v squared and so forth. This, of course, is v squared. And we could be thinking about a particle on a line. We don't need y and z in this. Just x is enough to illustrate the point. Particle moving in one dimension. Let me put back the speeds of light. All right? It's useful to put back the speeds of light in order to see what the non-relativistic limit is. The non-relativistic limit is basically the limit in which the speed of light goes to infinity. When the speed of light is bigger than any other velocity in the problem, that's the non-relativistic limit, the Newtonian limit. Lagrangian has units of energy. Mass does not have units of energy unless the speed of light is 1. But if the speed of light is not 1, we put in minus mc squared. Now it has units of energy. Phi I'm just going to leave that way. The field is defined. Oh, let's put a constant in here. Let's put a g in here. This constant is a constant called a coupling constant. It measures the strength by which the field affects the motion of the particle. So let's put a g in here. G can be anything for the moment. We don't know what it is. It might have a c in it, might not have a c in it, not important. At the moment, it's just g times phi, and phi depends on x and t. Now, let's of course, this is square root of 1 minus x dot squared over c squared. That's the Lagrangian with all the speeds of light in place. And now let's go to the non-relativistic limit. The non-relativistic limit, when c gets very large, we expand the square root. We expand the square root using the binomial expansion. 1 minus a small number to the 1/2 power, that just becomes, well, this thing becomes 1 minus x dot squared over twice c squared. The twice comes, the 1/2 comes, because this is something to the 1/2 power. I'm using that 1 plus epsilon, or 1 minus epsilon in this case, to the power 1/2 is just 1 minus 1/2 epsilon, plus things which are really very much smaller, because they will involve higher powers of the ratio of the velocity to the velocity of light. So this is what we get, plus tiny, tiny things. Let's erase this and write 1 minus x dot squared. Over 2c squared. Now we look at this and we try to find the biggest pieces, the pieces which are most important when the speed of light gets large. The obvious first piece is mc squared, just mc squared times 1. But mc squared times 1 is just a number. It doesn't do anything. When you start differentiating, it's a Lagrangian we're talking about. If you start differentiating it with respect to position or velocity, it doesn't do anything. It's just a number. So that term is of no interest. Adding a constant in a Lagrangian doesn't have any effect on the equation of motion. So the mc squared times 1 is of no interest. The next term has the speed of light canceling altogether. So it's part of the limit in which the speed of light goes to infinity, and it survives. It survives that limit. So the next term is the product of mc squared times x dot squared over 2c squared, and that's familiar. That's x dot squared m over 2. The c squares have canceled, and that's just the good old 1/2 mv squared, the non-relativistic kinetic energy. And what about this term, g phi times 1? That has no speeds of light in it, so it clearly survives. So we add minus, there's a minus sign here, minus g phi of x and t. And that's all that there is when the particle is moving slowly. And we just compare that with, the old-fashioned non-relativistic Lagrangian. The old-fashioned non-relativistic Lagrangian was kinetic energy minus potential energy. This is clearly kinetic energy, and that identifies for us g times phi as the potential energy of the particle, the potential energy of the particle in a field. G is just a constant. But in, for example, electromagnetism, the strength of the coupling of a field and a particle is just the electric charge. The bigger the electric charge, the bigger the force on a particle in a given field. So it's natural that there be some constant multiplying something about the field. We'll come back to this. But if you like, in this limit, the non-relativistic limit, and the only reason I do the non-relativistic limit is so we don't have to muck around with all these square roots of 1 minus v squared. Just to illustrate a point, this is effect, or this here represents the effect of the field on the particle. Okay. Now, what about the effect of the particle on the field? The important thing to understand is that there's only one action. The total action altogether, and the total action includes an action for the field and the action for the particle. The physics problem we're trying to do could be, we should draw a picture of what it is we're trying to do. We have a region of space and time, space, and we have a field in it. Let's just draw the field as a bunch of red mush. There's the field. And first of all, we're trying to find out how the field behaves. That involves knowing a Lagrangian for the field and minimizing Lagrangian for a field. And in addition, the mechanical system, or the system that we're studying, also happens to have a particle moving through it. So what we're trying to do is study a combined system of a field and a particle moving through the field. And we're trying to minimize the action, not just with respect to the motion of the particle, but with respect to the motion of the particle and the motion of the field, or how the field behaves in there. For that, very simple. We simply explore around changing the field, letting it wiggle in different ways, change the particle trajectory until we minimize the action, and that will give us the trajectory and the field that correspond to the principle of least action. Okay, so let's go and write the whole action, including the field and the particle. Well, first of all, we need an action for the field. We discussed this last time. I'm just going to write down what we wrote down last time. A simple case of it. The Lagrangian for the field that we wrote, L sub f stands for Lagrangian for the field, that we wrote down last time, or, well, the action. The action itself. The full action is the integral times d4x. d4x means dt and dx. It's an integral over the whole space-time region, x, y, and z, and t. And the thing we wrote down last time was the integral of 1/2 partial of phi with respect to t squared minus 1/2 partial of phi with respect to x squared. I'm finished with the speeds of light for the moment. I don't care about them anymore. I just wanted to keep track of them in this little exercise over here. But if we wanted to keep track of the speed of light, I think there would be a 1 over c squared here. All right. This is the Lagrangian for the field, and it doesn't involve the particle at all. But now we have to, or the action. This is the action for the field. But now let's also add to that the action for the particle. Here it is right over here. I'm going to take a very special simple case. You can work out the more complicated case, but I'm going to work out the case where the particle is at rest. Let's put the particle at rest. Let's assume for the moment that there is a solution to the equations where the particle is just at rest. After all, there are situations where an electron might be at rest, right? And ask what the additional term in the action is. We could make the electron move. It doesn't, but for simplicity, let's just take the electron to be at rest, not moving. That's the trajectory. And what is the action in that case? Here it is right over here. X dot is 0. This is just 1. MC squared by itself is of no interest. And so the Lagrangian for the particle, or the contribution to the Lagrangian from this piece over here, is just the integral of phi of x and t, but an integral along where? What kind of integral? It's an integral dt, right? This is just a particle. It's not a field. It's an integral dt. And it's an integral along the world line of the particle. But it involves phi. It involves phi. The reason the particle responded to the field was because the Lagrangian for the particle involves phi. The reason the field responds to the particle is because that same Lagrangian also has phi and the positions of the particles in it. So what do we add? How can we add this term here? I want to add it in a way that corresponds to an integral over space and time. How can I turn this into an integral over space and time? Oh, sorry. Let's go back a step. Let's go back a step. Where should I put this particle? For convenience and simplicity, let me just put it at x equals 0. It's a particle at position x equals 0. Then what do we put in here? Well, we put in the position of the particle, x, which is 0. Phi of 0 and t. Integral dt. Now this term here is just an integral over the world line. This term here is an integral over all space-time. In fact, the way I wrote it, space is only one-dimensional, so this would really be only a two-dimensional integral, but you know what I mean. Okay, how can I write this so that it looks like an integral over all space-time? Just to put it into one term. And the answer is simple. The answer is you use the Dirac delta function. You use the Dirac delta function. Here's the way you do it. This is what I want to get. Take phi at 0. The time is not important here. And let me write it in the following way. It's an integral over all space of phi of x times the Dirac delta function. The time dependence is not important here. It just goes along for the ride. Do you recognize this? When you integrate the Dirac delta function, the Dirac delta function is a very high spike of a function. It's a high spike of a function. It's 0 everywhere except at x equals 0. And so when you integrate the field with a delta function, you just get the field at the origin. You get the field at the origin, or the field at the place where where the delta function has its big spike.
Where does the dx cubed come from?
That's the integral over the volume. If this was a one-dimensional axis, we would just write dx. Let's take the case of what this, all right, I guess I really need to tell you what that delta function really means. What I've written is just delta of x. All right, let's be a little more precise. Let's call this delta 3 of x, d3x. Delta 3 of x means the product of three delta functions. Delta of x, delta of y, delta of z. Where is this function non-zero? It's non-zero when all three of these delta functions are non-zero. There's only one place where all three of them are non-zero. It's at x equals 0, y equals 0, or z equals 0. Okay. So what is it? It's a function of three coordinates, delta x, y, and z. It's a function of the three coordinates of space, but it only has a value at one point of space. And at that point of space, it's enormously big. When you integrate the field, let's write it out. Let's write it out in bloody detail. Integral phi of x, y, and z. I won't bother writing the time dependence. Delta of x, delta of y, delta of z. dx, dy, dz. That's what I've written here. That's the meaning of this symbol here. The triple delta function, and then integrating over all space. All right, how do you do this integral? This is not a very hard integral to do. Remember, whenever you integrate a function with a delta function, it gives you the value of the function at the origin, or at the place where the delta function is big, where it has its spike. We're just using the equation. Integral f of x, delta of x, equals f of 0. That's the defining property of the delta function. It picks out for you the value of the function at the place where the delta function has its spike. All right, so if I do the integral over x first, this one tells me to set x equal to 0. This integral tells me to set y equals 0, and this integral tells me to set z equals 0. So the whole thing is just phi of 0. That's what I've written here. Notice I also, in order to calculate the action, I also have to integrate it over time. The action was the integral of this phi over time. So in the action, we have the integral over all coordinates, d4x, that means dx, dy, dz, dt, phi of x and t, delta cubed of x. This delta cubed of x is doing nothing but picking out the value of phi at the spatial position of the particle. That's all it's doing. It's a trick just to write this thing here. It's a trick for writing the value of a field at a point as an integral. Why do I want to do it? Well, I just want to do it because I would like to add here plus, I missed something, I missed a G. Very likely. Because of this? Yeah. Minus G delta cubed of x phi of x. And now the whole thing is just one big integral over all space and all time. Here it is. And this thing inside the big square bracket is the Lagrangian. This is this thing inside the big square. This is the action equals. The action is now an integral over space and time, like any good field Lagrangian. It has the good old field action, and this term over here represents the effect of the particle back on the field. It's just this term over here for the special situation where the particle happens to be at rest. We could jazz it up so that the particle moves. This is phi of x and t. We could do that by making the delta function move around with time. That's possible to do, but it's not important right now. Okay, now let's go take this Lagrangian and work out the equations of motion for it. The thing inside the bracket is the Lagrangian, and let's work out the equations of motion. First of all, we have the derivative of the Lagrangian with respect to partial of phi with respect to t, d by dt. What is that? That's just equal. What is dl by d phi dt? It's just d phi dt, right? So this one is going to give us the second derivative of phi with respect to t squared. Sort of like an acceleration. We have a kinetic energy, phi dot squared. When we work out the equation of motion, we have something that looks like an acceleration of phi. Now, there are the other terms coming from d phi by dx squared, and they're exactly the same sort of thing. I'm going to erase this, and I'm just going to put in minus d second phi by dx squared. If that's all there was, I would set that equal to 0, and this would be a good old-fashioned wave equation, one-dimensional in this case. If we wanted to add more dimensions, we would add minus d second phi by dy squared, minus d second phi by dz squared, and we would set that equal to 0. That would be the wave equation describing waves of this thing phi. But now we have more phi dependence here. The Lagrangian depends on phi in another way. What happens if we differentiate the Lagrangian with respect to phi? Remember, what we're supposed to put here on the right-hand side is not 0. we're supposed to put the derivative of Lagrangian with respect to phi. That's the other side of Lagrange's equations, or the other side of the Euler-Lagrange equations. And we can see from here, the derivative of L with respect to phi at x and t is just g times the delta function. It's just g times delta cubed of x. So our equation is just that this is equal to g times delta cubed of x. Do you recognize this as an equation you may have seen before? Oh, there's a minus sign, I think. Was there a minus sign? Yes, there's a minus sign. Now, this is an odd equation. It's a wave equation, except on the right-hand side at one point, and only one point, there's something different. Something's going on at that one point which is different than the rest of space. What's going on? There's a particle there. It's affecting the equation of motion, but only at one point. Let's, just to try to make it a little bit familiar, let's suppose that we're looking for solutions of the equation. After all, the particle is standing still, at least in this example. If the particle is standing still, there might be a chance that there's a solution of the equation where the field itself doesn't change with time. Just the effect of the standing still particle affecting the field is likely to make a field which also doesn't vary with time. So we might look then for a solution to this equation in which phi is time independent. That means this is not there. And we can change the sign of everything. Plus, 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 plus. I don't know if you recognize this equation, Poisson's equation. This is the Poisson equation, for example, for the electrostatic potential energy, the electrostatic potential. It would sometimes be written as del squared phi is equal to a source on the right-hand side, a charge density, and in this case, the charge density is just a delta function. In other words, a high, sharp spike. So you see, now we're not really doing electrodynamics at the moment. We're doing a sort of simplification involving a scalar field instead of electromagnetic fields. But you see how it works. The same term in the Lagrangian, which tells the particle to move as if there was a potential energy g phi, in other words, which exerts forces on the particle. Also, that same term, when used for the equation of motion of the phi field, tells us that the phi field has a source. These are not independent things. The fact that the field affects the particle tells us that the particle affects the field, and with a specific simple example, it even tells us exactly how. Same parameter g. The parameter g determines how strong the effect of the particle on the field is, and it also tells us how strong the effect of the field on the particle is. So we have a nice little story there. Fields and particles affect each other through a common term in the Lagrangian. Okay, how might we, all right, let's just explore how we might change this a little bit. Let's go back to the one-dimensional case, just one space dimension. Then it's not, let's just make it one space. And this just becomes then second derivative of phi, a very simple equation. Second derivative of phi with respect to x squared is equal to g times delta of x. Simple equation. Supposing I wanted to put the particle someplace else. I didn't want to put it at the origin. I wanted to put it at x equals a. What would I do here? How would I change it? X minus a, delta of x minus a. Delta of x minus a has its spike when x is equal to a. Now supposing the particle were moving, that its position were a of t. all you would do is write delta of x minus a of t here. And what this would tell you is that there's a source of the field, but the source of the field is moving, and at any given time, it's at position a of t. So you see, we can accommodate a moving particle. We can accommodate a moving particle. The only thing is, if we did have the particle moving, we wouldn't expect the field to be time independent. If the particle is moving around, obviously the field will depend on time if the source of the particle is moving around. And so we would have to put back the other term here, minus d second phi by dt squared. There's no way we could get a solution with a time-independent phi, but where the right-hand side does depend on time. The only way to make it consistent is to put back the time dependence here. So a moving particle, or an accelerating particle, or a vibrating particle will affect the field, give it a time dependence, and you know what it'll do. It'll radiate waves. But at the moment, we're not going to solve wave equations. Well, we're going to do something else. We're going to spend a little bit of time just talking about the notation of relativity. The notation, I mean the mathematical notation that we use to make equations look simple and pretty, and not have to write every damn time we write an equation, second derivative with respect to x squared, second derivative is y squared, blah, 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 but have a neat notation. The notation was partly invented by Minkowski, partly invented by Einstein.
Question?
Yeah.
So this differs from classical in the way that the time term is used, is that correct?
This is what?
Differs from the for non-relativistic mechanics. Can we see that by looking at the time derivatives, partial derivative with respect to time, or is that actually not apparent?
Well, if we really wanted to do real non-relativistic, we would want to keep the v over c. You know, we would not want to go to the non-relativistic limit. But even in a non-relativistic limit, the right-hand side is time-dependent, and so it will create waves. But I'm not sure exactly what you're asking. But
I guess I would say, where's the relativity if I'm looking at that equation? I guess it's in the form of phi itself, is that right?
no, it's in the form of the equation of the left-hand side of the equation, c squared. No, it's in the form. All right.
From a unit analysis, G times phi has to be equal to energy.
Yeah, G times phi has to be equal to energy. Well, let's see. Let's see if we can figure out the units. I'll leave it to you. You'll figure out the units. The units of phi happen to be units of energy, and that means the units of G are dimensionless numbers. It depends on the dimension of space. That's not always true, but for the moment, this is not too important for us. All right, now we want to spend a little time just reviewing. For some of you, it'll be reviewing. For some of you, it'll be learning standard notation for relativistic vectors, four vectors, scalars. How do you make? We talked about this a little last time, but I want to come back to it. How you make scalars out of vectors, how you make vectors out of scalars, and how you condense notation so that things are neat. I'm sure that most of you know this, but we're going to do it anyway. All right. X mu, of course, stands for the four coordinates of space, time, space-time, and it's t, x, y, and z. Usually this is called 1, 2, and 3, and this one is called naught, but that's not important. Mu runs over four values. Notice now I'm going to pay attention now to where I put this index. I've put the index up on top, above. That's going to mean something to us shortly. At the moment, it doesn't mean anything. But this quantity, if thought of as a displacement from the origin, is a 4-vector. A 4-vector is a statement about the way it transforms, how it transforms under Lorentz transformation. Anything that transforms the same way under Lorentz transformation as x and t is called a 4-vector. I won't write it down for the moment. It's a 4-vector, has 4 components. Saying that 3 of the components are equal to 0, for example, that might be true. That would mean that it was a displacement that only involved 3 of the coordinates and not the 4th coordinate, but it's not an invariant statement. An observer, you may say that there was a displacement of an object which was purely time-like. In other words, it didn't move in space. I will say it did move in space. So the statement that a 4-vector has 3 components equal to 0 may be true in some frame of reference, but it's not an invariant statement that everybody will agree upon. But the statement that all 4 components are 0, that everybody will agree on, because all it says is that that vector is the 0 vector, no displacement at all. And we'll all agree that a 0 vector is a 0 vector. In fact, 0 transforms to itself under a Lorentz transformation. If all 4 coordinates are 0 before transformation, they're 0 after transformation. So that's the notion of a 4-vector. There are many 4-vectors. Differences of 4 vectors are 4 vectors. So differential displacements are 4 vectors, and so forth. Out of a 4-vector, we can make a scalar. A scalar meaning a thing which doesn't transform, which is the same in every frame. Now, I know we've done this before, and I'm going over old material, but nevertheless, let's do it. Out of a displacement, we can construct a proper time, d tau squared, and you know what that is. That's dt squared minus dx squared minus dy squared minus dz squared. And that has the property that it is the same in every reference frame. It doesn't have components. It only has one component, one value, and it's a scalar. So let's call it a scalar. This is a 4-vector scalar. Now, if a scalar is equal to 0 in one frame of reference, it's 0 in every frame of reference. Why? Because a scalar is the same as a thing which is the same in every frame of reference. So if in some frame of reference a scalar, whatever it's practically the definition of a scalar, the thing which is the same in every frame of reference. If it's 0 in one frame, it's 0 in any frame. So it's an invariant statement to say that a scalar is equal to 0. And here we have an example of how you make a scalar out of a 4-vector. That's very general. If you have a 4-vector of any kind, let's call it a mu. To say that it's a 4-vector means it transforms the same way under Lorentz transformations. Then the difference of the square of the time components and the space components are a scalar. I won't bother writing it. The difference, a time squared minus a space squared, are a scalar, is a scalar, and it's the same in every reference frame. We want a nice way to write that. I don't want to have to write a time squared minus ax squared minus ay squared minus az squared. Okay. For that, we invent a matrix. The matrix has a name. It's called the metric. In special relativity, it's usually denoted eta. Eta is the Greek letter, it's the Greek letter eta, E-T-A, and it looks like that. Eta is a matrix. Eta is a Greek letter. It stands for a matrix. And the matrix has 2 indices, mu and nu. But it's a very simple matrix. It's practically the identity matrix, but not quite. It has 3 elements which are equal to 1 on the diagonal, just like the unit matrix, but the 4th element is -1. The fourth element corresponds to time. -1, 0, 0, 0, 0, +1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. If I were to make this +1, it would just be the good old unit matrix. But it's not. Okay. Now, let's take this matrix. We're going to represent 4 vectors by columns. The column vector, for example, A mu, will consist of 4 entries, the time component, and the 3 space components, x, y, and z. And let's take the matrix and multiply it by the vector. We can either do it by matrix multiplication, or we can say, let's call this A nu. Let's use nu here. Nu runs also from 1 to 4. All right. Let's multiply the matrix by the vector. We can represent that eta mu nu A nu summed over nu. That's one way to write it. That's just this one, it's just matrix multiplication, but it can be represented by summing eta 1, 1 times A1, eta 1, 2, A2, and so forth. And this represents a new object, which we'll call A with a lower index here. Let's see what it is. Let's see if we can figure out what it is, what this A with a lower index is. It's not the original A. If this really were the unit matrix, and you multiply a vector, you would get back exactly the same thing. But not quite. The -1 here means that when you multiply eta by A, what happens? It changes the sign of the first term here, leaves everything else the same. And so we can write down immediately, without any further work, that A mu or nu, it doesn't matter, represents the column, the vector, let's call it the vector, minus AT, AX, AY, AZ. In other words, when I perform this operation, I simply change the sign of the time component. All right, so that's one piece of it's notation. This is purely a notational device. There's no real content in it. The second notational device, which no doubt you're also somewhat familiar with, is the Einstein summation convention. The Einstein summation convention says whenever you see a downstairs index and an upstairs index the same, in this case nu, it's automatically the rule that you sum over it. You don't need to write summation every time. So whenever you see a repeated index, as long as one of them is upstairs and one of them is downstairs, don't bother writing the summation sign. It's implicit in the conventions and in the notation. All right, so this operation here just has the effect of changing the sign of the time component. Now, I should warn you, depending on who's writing the equations, this can sometimes be +1, -1, -1, -1, or -1, +1, +1, +1. There are different conventions. I happen to like this one. Almost everybody else I know likes the other one, unless they're relativists. Relativists who study general relativity like the convention I use. So it's one of these conventions that never quite settled down, and it's like Republicans and Democrats, or Jews and Muslims. They hate each other like all hell, and there are those who use one convention and those who use the other convention. And when I'm with one group of people, I use one. When I'm with the other group of people, I use the other. And so far, I haven't been killed over it. Okay. We'll use this one. Now,
Question?
yeah.
Do you need the summation of that? Normal matrix multiplication just gives you a mu, lower mu, if you
No,
multiply.
matrix multiplication really means multiply this by this, plus this by this, plus this by this, plus this by this. Now, in this case, it's just trivial. But more generally, if eta was not the unit matrix, if it was something else, if it was some other matrix, say some general matrix, it would be this times this, plus this times this, plus this times this, plus this times that. So yeah, there would be a summation. But Einstein simply got fed up writing summation symbols. He just realized in every equation he was ever writing down, whenever there was an index, one upstairs and one downstairs, he was always summing over it. He cleverly said, I will invent the Einstein summation convention, and that's it. All right, good. Incidentally, an index like nu here doesn't actually have a value. It's a dummy index. It's a thing you sum over. This expression depends on mu, but it doesn't depend on nu. Nu is a summation index. A summation index is something that the expression doesn't depend on. It's just summed over nu, over nu. All right, now let's go one step further and look at the quantity A mu, A mu. Incidentally, these things have names. The vector with the upper index here is called a contravariant index. The upper index is called a contravariant index, and the thing with the lower index is called a covariant vector index. Upper, it's contravariant. Lower, it's covariant. But I don't use that terminology because I always forget which is which. I just call them upper and lower. Okay, it's easier to remember. All right, so A with an upper index and A with a lower index. And you go between them with this matrix eta. You can also go back, but I'll leave that to you to figure out how to do that. In fact, you do it the same way. Okay, now let's take A mu, A mu. This is summed over. Why is it summed over? Because by the Einstein convention, a repeated index, one upper and one lower, is summed over. So let's see what this means. This is equal to AT, AT plus AX, AX plus the same thing for Y and Z. I'll write the Y component, but I won't bother writing the Z component. Now, the space components of the covariant and contravariant vectors are the same. So this is just AX squared. This is just AX squared. And it doesn't matter whether you put it upstairs or downstairs. Likewise, this one is AY squared. Nope. Nope. Not yet. Why doesn't it have a minus sign? Because when you plug in the fact that the lower index here gives you minus AT, this becomes minus AT squared. In other words, this notation here says sum, literally sum, no minus signs in here. But the minus sign comes in for the simple reason that when you lower the index, it's called lowering the index. The operation of lowering the index changes the sign of the time component. So AT upper times AT lower is minus AT squared. So you don't have to, in fact, you mustn't put any extra minus signs in here. All you have to do is remember what the meaning of A upper and A lower are. Well, this is exactly the quantity that we think is a scalar. It's the difference of the square of the time component and the space components. In other words, It's this quantity here, except with an overall minus sign. It starts out with a minus sign here and a plus sign here. But whatever it is, it's clearly a scalar. It's clearly a scalar. And so we see an example of building scalars out of vectors. And how do we do it? We do it by soaking up all the index. It's called contracting the indices. Contracting the indices means when you see two indices which are the same, an upper and a lower, you sum over them. This quantity with an upper and a lower index summed is a scalar.
So why don't we write A sub mu as a row matrix?
Say it again?
So why don't we write A sub mu as a row matrix to be consistent?
Oh,
with
we could. I think we could. But we probably want, it doesn't, you're right. I think if we wanted to be purists, we might, but I think we would. But this is what it is. This is what its components are. This is what its components are. Okay? And this thing is a scalar.
Work for normal matrix times vector multiplication.
What's that?
If you multiply a matrix times a column, you get a column like this.
That's true. Yeah, you're right. You're right. Okay. Right. Right. Okay, I'm not going to, we know what we did. We know exactly what we did. Yeah. We could also write this in another way. We could write this, since A lower mu, well, let's change the summation index here. Let's call it A nu. I haven't changed the expression. I've just changed the dummy index there. But now let's look, no, I didn't want to change it. I wanted to leave it. Mu. But now what I want to do is use for A mu, it is eta mu nu, A nu. A mu is equal to eta mu nu, A nu. So here's another way to write it. You sum over mu and nu with the matrix eta. It's the same thing. All it stands for is A times squared minus A space squared. That's all it stands for, but it's a neat way to write it where we don't have to keep rewriting x squared, y squared, z squared, and so forth. So that's the first notational device.
So is it true that when you use the Greek letters for subscript and superscript, it always refers to the whole?
Yeah. Whenever you use the Greek index, mu and nu, it refers to all four components. If you want to refer just to the three components, you usually use Latin indices, sometimes I and J, sometimes M and N, depending on who's writing. Yeah, right. Okay, so this is a scalar. Now, what about, let's consider something else. Let's take two 4 vectors. Take two 4 vectors A and B. A mu, B mu. That looks like it might be a scalar. It's got no indices. All the indices are summed over. Question, is it a scalar? Yes, it is a scalar. But let's prove it. Oh, well, we need one thing to prove it. To prove that it's a scalar, all we really need is the statement that the sum of two scalars and the difference of two scalars is also a scalar. If you have two things, you and I agree upon what they are because we're in different frames, but we agree. We can add them and subtract them, and we'll still agree about the values of the sum and difference. So sums and differences of scalars are scalars. Let's prove that this is a scalar. Right? That's easy. All you do is you write A plus B mu times A plus B mu. Mu. Now this is a scalar. A plus B is a 4 vector. And if you take any 4 vector and contract it with itself, it's a scalar. So this is a scalar. Now subtract from this. Take a look at what we have. We have an A mu, we have the A's, the AA terms and the BB terms are the same in both sides. All that's different is the AB. So we'll be left over when we do this with an A mu, B mu. Oh, incidentally, here's something to prove. This is the same thing as A mu, B mu. It doesn't matter, you can put the ups downs and the downs up, you get the same thing. The difference between these two things is just 4 times A mu, B mu. So here's a scalar, here's another scalar. The difference between them is basically just A times B, A mu, B mu. So if I take any two 4 vectors and contract them in this way, I get another scalar. So it's a slight generalization of just saying that, that A is a scalar. Take any 4 vector with any other 4 vector, it's also a scalar. It's also a scalar.
Is there any analogy one can draw to like the dot product of vectors?
What's that?
The dot product of normal vectors and the cross product?
Yeah, the dot products. The dot products, except with a funny minus sign. It's the Lorentz or the Minkowski version of the dot product. Right. And the eta facilitates the change of sign. That's all that's going on. Okay, now, let's take a scalar field. Let's take a scalar field, phi of x. X now stands for x and t. If I write a thing like this and I don't say otherwise, it really means it's a function of all 4 coordinates. And let's consider the difference of phi at 2 neighboring points. If phi is a scalar, and we consider its difference at 2 neighboring points, and we agree on the values of phi at each of those points, we will agree on the difference between them. And so, I need a theorem. I need a theorem. It's a theorem which I won't prove. I will tell you the statement. It's something you can easily prove by yourself. Here's the theorem. Supposing you have, let's see how to say this. Yeah. Supposing you have a known 4 vector. To say it's a 4 vector means that it transforms in a certain way. It's not just a statement that there are 4 components. It means when you transform it under Lorentz transformations, it transforms in a certain way. Supposing you have a 4 vector, number 1, and number 2, another quantity, b mu, such that then when you multiply a mu times b mu and sum over mu, you get something which is a scalar. In other words, you get something which doesn't depend on the frame of reference. You know this is a 4 vector and you don't know about this. Then it's possible to prove that if you know that this product is independent of reference frame, that B is also a 4 vector, that it also transforms as a 4 vector. We'll use that in a moment. It's sort of obvious. If A is a 4 vector and A times B is a scalar, then B is a 4 vector. Not too hard to prove. Okay, now let's take the difference of phi at 2 neighboring points. If we agree about the values of phi, we will agree about the values of their difference. And so we will say the difference is something which we will agree about. We'll call it, for the moment, a scalar. All right, what is the difference between phi at 2 neighboring points, infinitesimally separated? The answer is you differentiate phi with respect to each of the coordinates, multiply it. This means derivative of phi with respect to t times dt, plus derivative of phi with respect to x times dx, plus derivative of phi with respect to y, and so forth. This is the small change in phi in going from one point to another. Well, phi is a scalar, and so we will agree about the value of the difference of phi. Dx itself is clearly a 4 vector. It was the basic 4 vector that we started with. Small differences, small displacements. This is a 4 vector, and the whole thing is a scalar. What does it tell you about this? It tells you it's a 4 vector. The derivative of phi with respect to coordinate It's a complex of 4 quantities. It stands for derivative of phi with respect to t, derivative of phi with respect to x, and so forth.
So the upper mu in the denominator is like a lower u.
Yeah.
Is that the notation?
Yes, that's what we're finding. That's what I was going to say. Right. Right. In order for this to make sense as a product, as a product of this type, this had better, the d phi by dx had better correspond to a covariant vector if the derivative corresponds to a contravariant one. So what we find out is that derivatives of phi with respect to x, the complex of them, the set of them, form a 4-vector, but they form the covariant components of a 4-vector. The covariant components like a mu. All right, so now we know something else. We know that derivatives of a scalar with respect to x mu are a covariant vector, and it's sometimes just written as d sub mu phi. The index being a lower index here to indicate that it's a covariant thing. Good. Well, now we can use a notational device to invent d mu phi. What is d mu phi with the upper index here? It's actually just exactly the same things here, except the time component having the opposite sign. Okay, so let's write out the meaning of these symbols. D mu phi stands for the complex of things dt phi, or d phi by dt, and d phi by dx, y, and z. What about this new symbol, d mu phi, with the index upstairs? It's the same set of things, except minus d phi by dt and d phi by dx. All right, so it's a bunch of notation, but all it's keeping track of is squares of time components minus squares of space components, or squares of space components minus squares of time components. That's all it's doing, but it's neat. Finally, we can construct a new scalar. Phi was a scalar. The derivatives of phi form a 4-vector, but now we can form a new scalar. The new scalar is composed out of these two or out of the 4-vector. What is it? We just take d mu phi, and sum over mu. What does it stand for? It stands for something we wrote down earlier, d phi by dt squared minus plus d phi by dx squared, d phi by dx squared, plus the same thing for y and z. In other words, it's the thing we wrote down with a minus sign. There's an extra minus sign here. It's the thing that we wrote down for the Lagrangian for the scalar field. Okay. What is this telling us? It's telling us that the scalar field Lagrangian is a scalar. The Lagrangian itself, not the scalar field. The scalar field was a scalar because we said it was a scalar. It means it didn't transform when you Lorentz transformed it. But this little exercise here in notation tells us that this quantity here is also a scalar. Why is that good? Why is it good that the Lagrangian is a scalar? And the reason...
Is that Lagrangian or Laplacian?
No, this is not the Laplacian. This is the Lagrangian. The Laplacian is composed out of second derivatives. These are squares of first derivatives. The Lagrangian, okay, in this language, the Lagrangian for the scalar field is equal to minus 1/2 d mu phi d mu phi. And it is just time derivative squared, 1/2 time derivative squared minus space derivatives squared. Okay. We could add things to this Lagrangian. I won't do it now, but we could add other things to this Lagrangian. But the rule is the Lagrangian should be a scalar. What's the value of saying the Lagrangian is a scalar? It says the action is the same in every reference frame. If you have a scalar, a quantity which doesn't depend on frame of reference, and you integrate it over all space-time, then the result doesn't depend on which frame of reference it's been evaluated in. So if your principle of physics is the principle of least action, and the action doesn't depend on which frame it's written in, then the same action principle will give you equations of motion in each frame which have the same form in every reference frame. In other words, it'll give you equations which are invariant under Lorentz transformations. So much of studying field theory is really the construction of invariant Lagrangians, construction of various kinds of fields, scalars, vectors, other kinds of fields which we haven't discussed yet, tensors, spinors, constructing out of these objects Lagrangians which are scalars. Why? Because you want to build equations which are the same in every reference frame. You want your equations to be Lorentz invariant. That's the, and we'll use that. I mean, we're going to use that over and over and over again in what follows. The tricks of index manipulation. But then when we actually come to write down real equations that we have to solve, we of course have to know what this means. We have to know that it means a time squared minus a space squared. Okay, that's notation for you. Yeah.
When we were doing Lagrangians in Newtonian physics before, we didn't require the Lagrangians to be invariant under different motions. So why is it?
We didn't talk much about it. Right, we didn't. Now, we didn't talk about relativity very much, but there is a non-relativistic version of relativity. Yes, there is. The special theory of relativity entails two things. It entails the rule that the laws of physics are the same in every reference frame, and second, that it's a law of physics that the light moves with a certain velocity. Okay, combine them together, light moves with the same velocity in every frame. If you leave out the statement about light, then ordinary Newtonian or Galilean physics, F equals ma type physics, does have a relativity associated with it. It's not the relativity of Lorentz transformations, it's the relativity of the limit of Lorentz transformations when the speed of light goes to infinity. Let's talk about that for a minute. We didn't talk about it. Let's write down Lorentz transformations and take the limit. X prime is equal to x minus vt divided by square root of 1 minus v squared over c squared. T prime is equal to t minus xv over square root of 1 minus v squared over c squared, but I'm not quite right. I think I have to divide this by c squared to get the units right. This is the, and of course we have two others. Y prime is equal to y, and z prime is equal to z. All right, we didn't speak much about this, but we could take the limit of these transformation rules as the speed of light gets very, very big. What happens to them? Well, the square root in the denominator here just becomes 1. So it's just x prime is equal to x minus vt. Well, that's familiar. That's just the change of coordinate before anybody ever heard of the special theory of relativity, this is what they would have written down. What about this one over here? Again, taking c to infinity, this becomes 1. But now we have x times v over c squared. When c goes to infinity, this goes to 0. And it's just t prime equals t. So yes, there is an invariance of non-relativistic Newtonian mechanics. It's called Galilean invariance, and it requires the equations to be invariant under these replacements. This replacement is trivial. It just says that all observers, all frames of reference share the same time. Simultaneity is the same for everybody. So that's easy. And this is just the usual change of reference frame from one inertial frame to another. So when people say that the equations of physics are the same in every inertial reference frame, it's a statement of relativity. It is a statement of relativity. And in fact, when we write down F equals ma, typically those equations are invariant under this. We didn't discuss it, but they are. Other questions?
The transformation properties for a covariant and a contravariant, the difference is just a change in v, the sign of v?
No, not quite. Let's do it. Okay. Almost. Almost. Well, let's work it out. A prime t is equal to at minus v ax squared 1 minus v squared and so forth. And a prime x is, of course, ax minus v at. Usual thing. Okay, now we just write that a prime t is the same as minus at here. At here is the same as minus at here. A with an upper index t here is the same as A with a lower index t here. What about A superscript x? That's the same as A lower superscript x. Only the time components change. And so these just go downstairs. Okay, so let's see. So I think you're right. I think that it seems to just change the sign. Yeah. Yeah.
I'm a little confused about when a scale, what I think of as a scalar valued function with some coordinate system, when that would not be a scale. In other words, define any function there, it might have no physical meaning whatsoever, and you just say, well, when you look at it in its other coordinate system, that function at this point transforms according to Lorentz equation. It would just seem like anything.
No. Energy density.
Pardon?
Energy density. Energy density. Energy density of a gas. The energy of density of a gas in a frame of reference in which the gas is in a box and the box is at rest, there's a certain energy density. If you're at rest and you look at the energy density, there's a certain energy density. If you're moving fast relative to that box, the energy density in that box is a lot larger. So energy density is something which we won't agree on.
So I guess what I would say then is that what you mean is that a scalar function is some physical quantity that in every reference frame you describe as something.
Well,
And that transforms according to, okay.
right. Right. When I say we agree about its value, I mean if we measure it, we agree about its value. Right. Yeah. I don't just mean we agree because we're nice to each other. I mean we agree because we made the measurement and we compare the measurements. Right. So energy density is a good example. There are lots of them. The components of the forward velocity of a system, time component of a forward velocity is not the same in different reference frames. Other questions? Okay, if not, we'll move on. This is all very easy stuff. It's very easy. It's just notation. But until you learn it, it's a little bit unfamiliar. Let's talk about waves. Let's look at the wave equation. Let's look at the wave equation and solve it. Let's solve the wave equation. Let's imagine we have some wave field, and it satisfies. Oh, let's even begin by writing down a Lagrangian. Let's write down a Lagrangian. We've already written down a Lagrangian, but I want to write a slight extension of it. Here it is, d phi by dt squared minus d phi by d. Now I'm going to write it out in detail because also y and z, I'm not going to write down the y, then they come in with the same sign as this. We always put a 1/2 there in front of the whole thing. Okay. And I'm going to add one more term. The one more term is also a scalar. It does not involve derivatives. It's a function of phi. And the simplest function of phi that I can think of, well, we could just add phi. That would be a simple function of phi. But it's going to make a slightly more complicated one, phi squared. Okay, so including the 1/2, we're going to write with minus a parameter which I'm going to call mu squared, phi squared over 2. Oh, no, it's already got a 2 in it. Now this is the field theory analog of the harmonic oscillator. That's all this is. It's the field theory analog of the harmonic oscillator. If we were talking about a harmonic oscillator and we called the coordinate of the oscillator phi, we call the coordinate of the oscillator phi, we would write down phi dot squared over 2 for the kinetic energy, and then for the potential energy minus a spring constant, which I'm calling mu squared, minus mu squared phi squared over 2. This would be the good old harmonic oscillator. And the only difference is it now has some space derivatives in the, in the Lagrangian. Let's take this Lagrangian, work out the equations, and then solve it, find its solutions. Well, it's first of all derivative of L with respect to time derivative. That's just d phi by dt. Then we differentiate it with respect to time. We get second derivative of phi with respect to t squared. This, of course, is the analog of the acceleration term, the acceleration in F equals ma. But then we get minus d second phi by dx squared, minus same thing with y, minus same thing with z. And that has to be equal to dl by d phi. So that's equal to minus mu squared phi. When you differentiate mu squared phi squared with a factor of 2, you just get minus mu squared phi. Or if we want to put everything on the left side, let's put everything on the left side. Plus mu squared equals 0. This is a nice simple equation. It has a name. Anybody know what the name of this equation is? No?
the Klein-Gordon equation.
Yeah. This is the Klein-Gordon equation. Klein and Gordon, I don't know if they were connected with each other or not, but I have a feeling Klein was a German and Gordon was probably a Brit, so they probably were not collaborating. But in any case, in some combination or another, they wrote down this equation. This was their attempt before Schrodinger to write down the equation for a quantum mechanical particle. They made the mistake of trying to be relativistic. Had they not tried to be relativistic, they would have written down the Schrodinger equation and been very, very famous. They wrote down the relativistic version of it and became much less famous. Famous among physicists, but not famous outside of the physics world. Only one person here knew that it was the Klein-Gordon equation. The Schrodinger equation is somewhat similar, but it only has a first derivative with respect to time, and it has some i's in it. But this is called the Klein-Gordon equation, and its connection with quantum mechanics is not important right now. What we want to do is solve it. There are lots of solutions to it, zillions of solutions, but they're all built up out of plane waves. The solution to this kind of equations are sums of plane waves. So let's write down a plane wave in exponential form. It's useful when thinking about oscillating systems to pretend that the coordinate is complex and at the end just take the real part of it. Right? We do that for the harmonic oscillator. We do it for all sorts of oscillating systems. Look for solutions which we allow to be complex functions and later take the real parts. I'll give you an example as we go along. All right, what kind of solutions are we going to look for? We're going to look for solutions which first of all oscillate. I can't remember if I want plus or minus here.
Minus for positive energy solutions.
Yeah. E to the minus I omega t. That's an oscillation with time with frequency omega. And now we're going to look for solutions which oscillate in space, which means they're e to the I kx of some type. E to the I, and we can write here kx times x plus ky times y plus kz times z. Well, these are three numbers. Kx and ky and kz are just three numbers. They're called the wave numbers, or the wave vector, kx, ky, and kz. And this is the form of a solution that we'll look for. We'll see. Maybe there is no solution like this. We'll check. All right. First of all, we can rewrite this in a kind of neat way. We could rewrite it as e to the I k mu x mu. Where does that come from? Well, if I think of k as a 4 vector with components minus omega, do I want minus omega? I think so. And kx, ky, and kz. If we think of the 4 components of a complex of things involving omega, kx, ky, and kz, and I group them together in this form here, call them, think of them for the moment, they may not really be, they are actually a 4 vector, but think of them as defining a 4 vector. Then what's up in the exponent here is just k mu x mu. Time component omega times t, x component of k times x. So it's a nice little notation, but I'm not going to use it now. I'm just going to use it in this form here. Let's see what happens if we try to solve this equation. What is the second derivative of phi with respect to t squared? Well, what happens when you differentiate an e to the I omega t with respect to time twice? that'll multiply what you have here by minus omega squared. So let's call this this is our guess at phi. All right. What happens if we differentiate it twice with respect to t? We get minus omega squared times phi. What happens if we differentiate with respect to x? We get kx squared. With respect to y twice, ky squared. And so altogether we'll get minus omega squared plus kx squared plus ky squared plus kz squared. But we're not finished. We still have plus m squared here. So there's plus m squared phi equals 0. Well, it's very easy now to find the solution. You simply say omega must equal the square root of kx squared plus ky squared plus kz squared plus m squared. In other words, you just set what's in the bracket here equal to 0, and you have a solution. This is just telling you what the frequency is in terms of the wave number. Frequency, square root of kx squared plus ky squared plus kz squared plus m squared. Okay? That's the solution of the Klein-Gordon equation. There are two possible solutions. A square root like this can be plus or minus. It'll solve the equation whether you put plus omega or minus omega here. And of course, for every kx, ky, and kz, there are two solutions with plus omega and minus omega, or the plus or minus roots of the square root. Those are the solutions of the Klein-Gordon equation. And we're going to come back to it many, many times. This is the quantum mechanics, or this is the classical field version of an equation which describes a quantum mechanical particle with mass m, energy omega, and momentum k. This is E equals square root of p squared plus m squared. There's some Planck's constants in there that I didn't tell you about, but they're there. All right, so these equations aren't hard. They're simple. They're linear equations. You add solutions. And at the end of the day, after you've constructed your solution in this way, you can take the real part of it, and the real part of it, if the field is supposed to be real, then if it's supposed to be a real number, you just take the real part of it. Okay, any questions? We're getting, we're moving along now, and we're talking about real stuff. Yeah.
So where did the Klein-Gordon equation come from? I mean, did you do something to the Lagrangian to take it?
Here's Lagrangian. I made up this Lagrangian. If you look for, okay, good. This is pretty much the unique Lagrangian which would lead to linear equations. A linear equation. We'll come back to why we're looking for linear equations, but for the moment, this is just an example. At the moment, it's an example.
The next step going from that Lagrangian to the Klein-Gordon equation, it's like you took the next derivative of each term with respect to the variable.
Yeah. Derivative of Lagrangian with respect to d phi dt, that's just d phi dt. And then you differentiate that with respect to time.
Right.
You know, same thing.
And you add the second partial with respect to x and then with respect to y.
Yeah, remember what the rules are. Okay, let's write down the Euler-Lagrange equation for a field. D by dx mu. All right, we'll now write them in a neat form. D by dx mu of partial of L with respect to d phi by dx mu, and that means sum over mu, equals or minus partial of L with respect to phi is equal to 0. D by dx mu, this is a covariant index, a downstairs index. In the denominator here, you have a d phi by dx mu. That makes this an upstairs index. But this is of the form of a lower index times an upper index. And you can see that this equation has some nice relativistic structure. Upper indices and lower indices contracted, and everything is a scalar. Yeah.
What in nature obeys the Klein-Gordon equation?
Scalar particles, the Higgs boson. The Higgs boson. Let's go back to something else. Let's go back to the action for a particle. We wrote. I made this up, of course. I made this up, but I was using some rules. The rules are that it should be relativistically invariant and fairly simple. So we generalized this thing times the square root of 1 minus v squared. We generalized and put in minus m plus phi. That's a guess. I mean, that's something you can write down. Can you think of anything else? Yeah, you can think of lots of other things. But this is one thing you could write down. Now notice that this has an interesting property. If for some reason or another phi was not equal to 0, for some reason or another you had a region of space in which phi was not equal to 0 but was equal to some fixed value for some reason, for whatever reason, then effectively this particle will move with a mass m plus phi. For all practical purposes, if phi is a constant, it just shifts the mass of the particle. Well, it's even possible that you might have a massless particle with no term at all, and the entire mass is due to some field not being equal to 0 in some region of space. If for some reason there's an environment in which phi is not equal to 0, it can not only shift the mass, it can create a mass for a particle that didn't even have one to begin with. That's the nature of the Higgs boson. It creates mass. In this sense, in roughly this sense. And because it creates masses for particles, such as quarks and other particles, because it creates masses, the presence of those particles will, will react back on the field and create field. Particles create field, field affects particles. Higgs boson is a particular case.
When you said you take the real part of the solution, does that mean the imaginary part adds up to 0, or does it mean you just throw away?
No, it just means you write it as the sum of a real part and imaginary part. Let's write it. Let's take a solution. All right, so where was our solution? I lost it. Well, it was of the form e to the I omega t minus k dot x, let's call it, minus k dot x. The I multiplies everything. Okay, so this is equal to cosine of omega t minus kx plus I sine omega t minus kx. Both the real and imaginary parts. If something is equal to 0, we went through an exercise, set all of this equal to 0, If all of this is equal to 0, it means both its real and imaginary part are equal to 0. So both the real and imaginary part are solutions of the equations. A construction like this gives you two solutions, two real solutions, cosine omega t and sine, cosine and sine. You can add them together. You can add them together with real coefficients too, and they're still solutions. But you know, exponentials are a neat trick for facilitating taking derivatives. That's the reason we used exponentials, not because the field is imaginary or complex, but because it just helps us do the algebra of taking derivatives. But once we have a solution like this, the real and imaginary parts are both separately solutions. They're both plane waves. They're waves, and what are they? They're 90 degrees out of phase. If this is a wave that moves down the axis like this, such that at time t equals 0, the wave peak is located here, that's the cosine, then the sine is just another wave that's displaced like that. You can add them together, you can subtract them, and they're still solutions. Okay. Any other questions? Yes.
Can you explain the superconductor case?
What? Who? Where did that come from?
From the giving particle's mass. Particles acquire mass
Yeah.
when a field appears.
Well, I mean, yeah. Can I explain? Yeah, I can explain superconductor, but not yet. We haven't done any electricity, any magnetism. The superconducting case is a situation where the electromagnetic field gets a mass. And it gets a mass from a similar thing like this, but not at this point. No, I don't think you want me to, no. Yeah, it's certainly a connected phenomenon, but we haven't gotten into the answer is that it is an effect where a scalar field, where the presence of a scalar field affects the photon and gives it a mass, but not yet. Yeah. Yeah.
So what you've said about the Higgs boson these have been mathematical conclusions. Is there any way that it's possible to visualize how a Higgs boson creates mass?
Here it is. Here it is. Here it is. Here it is.
I mean, a physical way. Do we think of a particle flying through space somewhere and spitting out masses as it goes along, or what?
No, it's just, this is what phi does to it. It shifts its mass. That's it. There's no other, there is nothing else. That's it.
So different masses, different coupling constant?
Yeah, that's right. I didn't put the G here, did I? So, right, so different coupling constants could lead to different masses, right? And in fact, they do. The strength with which a particle couples to the Higgs field will determine its mass.
When you compute its momentum, phi is the mass term.
Yeah, that's right. But in every respect, it functions as a mass term. No.
And if the Higgs field were 0, all particles would be massless?
Not all particles, no. Quarks would be. Z bosons, W bosons would be massless. The Higgs boson wouldn't be. And protons and neutrons wouldn't be massless. Protons and neutrons do not get their mass from the Higgs phenomenon. And electrons and neutrinos would be massless. Electrons and neutrinos would be massless. Protons and neutrons, not. Quarks, in some sense, yes, but protons and neutrons, not. Right. If the Higgs field went away one day, electrons would become massless. That would be a disaster for atoms because the size of an atom is governed by the inverse of the mass of the electron. And if the mass of the electron were to go to 0, the atom would become infinitely big, and that would not be good for you. But protons and neutrons would be virtually unaffected, very, very weakly affected, not very much. Right. Yeah. Well, I mean, it is true that a world without a Higgs boson would be a bad world for your survival. Many, many things would go wrong. And, as I said, not the least of which would be the electron would become massless, and when it did so, atoms would just have the electron would become completely unlocalized. Okay.
For more, please visit us at stanford.edu.